Okay, welcome back. So this is the fourth lecture for week 8. We have been discussing about RLHF, and this is a continuation of our discussion in the last lecture. Okay, so we will talk about how the training is done in RLHF, and we will also talk about proximal policy optimization very briefly, PPO. So this is where we were. We were saying, okay, we will have a data set of prompts. I'll have a language model that is given a prompt will do some completion. I have a reward model that will give a reward. But how do I use this reward to update the parameters of my language model through an RL policy? So let's see. So I want to ideally, so I sample some prompts, right, and for each prompt I do some generation, and I get a reward, right. I want to maximize the reward, right. That's what I want to do. Okay. So I want to maximize this reward. So the typical way of doing it, you do gradient ascent, right. You want to maximize this quantity. You say, okay, so my parameters at t plus 1 will be parameters at previous time plus alpha learning rate times the gradient of this whole thing, right. Okay. Now, of course, the challenges are what if the reward model is not differentiable, and then there is an expectation sign. So how do you estimate this expectation, right. So let's see. So first of all, I want to do a gradient of this thing, gradient of the expectation over the reward, where as said is sampled from this the language model. Now I put it back the definition of expectations. Expectation is nothing but over all possible generation, what's the reward of the generation times the probability of that generation. That's the expectation, and I have RS here. Yeah. Now, because of the linearity of gradient, because RS directly does not depend on theta, RS is coming separately from a separate model, I will say, okay, this can be written as summation as RS delta theta p theta s. Okay. Now, this is where there is a very standard trick in RL that is used, like that's famous for reinforce. So what is that? This is called log derivative trick. So what is the trick? So this is like people know that and they just use it directly. So what is the trick? They said, okay, let's say you try to find the derivative of log p theta s, right. So what will be this? So okay, delta theta log p theta s, I will do 1 over p theta s and delta theta p theta s. That's the chain rule of derivation. Okay. Now from this I can say, okay, so that means I can write delta theta p theta s as this whole thing times p theta s, right. I mean, no big deal. If you know this, you know this. So then that means delta theta p theta s can be written like this by using this chain rule of derivation. And then what people do is whenever they have delta theta p theta, they substitute this quantity. Okay. So let's do that. So we will get sigma s RS delta theta log p theta s p theta s. That's what I'll get. Now, once you understand this quantity, now you think about it, this is nothing but expectation of this thing, right, summation s p theta s times something. So expectation of this quantity. So I can put back the expectation sign. So I'll say, okay, now this can be written as expectation over R s hat delta theta log p theta s hat. Okay, for all possible generations. Okay. Now that we are here, right, so R s hat delta theta p theta s. So we say, okay, now how do we approximate this expectation? So a very standard way of approximating this expectation is, okay, I'll take m samples, right. So I'll take m samples and I'll compute this value for all m samples. So S1 to Sm. So RSI delta theta log p theta Si for all m samples and take an average. So mean of that 1 by m. Okay. So, I have my expression. So, that means, so that theta t plus 1 is theta t plus alpha times this thing. So, alpha times 1 by n summation r s I delta theta log theta s I. Okay. Now, see, s I is my completion and r s I is the reward. And if for the completion the reward is high, that means I will take gradient steps to maximize this p theta s I. And if r is negative, so then I will take steps to minimize this p theta s I, right. So, that is how you can understand this particular formulation. Now, you can also see what is the connection of this with the normal cross entropy training, right. So, if you remember in cross entropy also your formula is very similar. You have theta t plus 1 is theta t minus learning rate alpha, and then you do the derivative log, what is your loss, minus log p theta, and this minus minus you can put plus. So, you see you have exactly same equation, except that this is now multiplied with the reward. So, here there was no reward, here there is a reward, right. Otherwise, they are very similar, but there is also a subtle difference across the two things, right. So, here, so what is the difference? Think about it. So, here when we do the cross entropy loss, this S is nothing but the ground truth completion. So, you are doing next token prediction and you know the ground truth. You want to predict that. What is the probability of this ground truth token prediction, right? While what is SI here, we do not have a ground truth, we are just generating. So, this is like you are exploring and you are finding a reward for that and using that to train, right. While here you knew this is the ground truth and you are saying that I should predict that with a high probability, right. So, that is another difference, that you have a reward. Second, it is not a ground truth thing, it is just an exploration by the policy, right, and you are giving a reward to that. So, it can be positive reward, negative reward, depending on, right, I mean what is your completion is good or bad, right. Okay. So, this looks now, I mean if you see in terms of coding, it is not too different from what you do in the normal cross entropy based training. Now, there is one more thing that you have to do for fine tuning with RL, that is called KL penalty. So, what is the idea? So, you say okay, I have a data set, I have a language model, I have a RL model that I am training, but what may happen, it starts generating things by which it gets good rewards, right. So, reward model is just a model, language model. Now, there can be some shortcuts to getting good reward, like maybe the model is trained such that if you have a longer response, you get a high reward. So, then what may happen, it can learn a shortcut trick to maximize the reward, and this is what is known as reward hacking, right. So, fooling the reward model or reward hacking. So, it may just go haywire and just learn how to optimize my reward without caring about good quality generation, right, that can happen. So, how do I avoid it? How do I avoid it going haywire and just trying to fool the reward model? So, for that we do another thing, we say okay, I had the initial instruction fine tune model, right. Now, I am training this. So, it had some parameters, it had some parameters. Now, for the given prompt I can also do a generation, I have this generation, right, I have the generation y. I can find out what was the probability of generation from the initial language model. So, base model, what is the probability of generation from this policy model that is currently being trained. See, this is already frozen, right, this is frozen and this is what is getting trained. So, I can compute the KL divergence between the probability distribution being given by the RL policy and the one given by the initial language model, the base model. And I want that not to be high. I don't want it to be diverged too much from the base model, right. So, that is why what I do, I have a reward based on reward model, plus I add this KL divergence term, that okay. So, do not go away too much from the base model, right. And this is like one of the pictures was shown in the paper, that if you do not use this optimization, do not use the scale divergence term, just use the reward model, what happens? Slowly, the RL model goes away from the supervised baseline. It thinks that it is predicting a high reward, but the actual preferences are very low. Okay, so it learns to fool reward model. So as per its model, it is getting a high reward, but if you get humans to rate the preference, you get very low scores, right? So and this is okay if you go nearby to the base model, but if you go too far, then you actually regress, right? You go down. Your number of things that are preferred to reference, they go down, right? If you go too much far away from the model, and that's why this penalty, the KL divergence penalty, actually helps. So together, the reward model score and the KL divergence penalty, that defines your final reward. Okay. So this is what I will do. So I'll take a prompt, I'll get a completion, I'll get a reward, plus I'll get what is the probability distribution, the KL divergence between the initial language model and the RL model for the completion, and this becomes my final reward that I will optimize for, right? And this happens very similar to what we saw. Only thing changes that instead of just putting RS is now reward model score minus the KL divergence term, this particular thing. Okay. Now I'll just briefly talk about PPO. That's a slight more involved formulation of the simple reinforced way of doing RL that we said, and that's also quite popular in the community. So in PPO, we start thinking in terms of trajectories, right? So remember what we said about trajectories. You have an initial state, you take an action, go to next state, next action, and so on, right? And you can compute the probability of a trajectory. You can compute the overall reward for the trajectory by saying reward at each time point and putting some discounted gain, right, for future. Now, what are the trajectories in case of language model training, right? Because we said every prompt is sort of independent of each other. So if you want to define trajectory, it has to be on the same prompt. So in the same prompt, if you start generating one token after another, that's a trajectory that you can have, right? So like here, so suppose this is my prompt, where is Shanghai, and this is generation, Shanghai is in China. So your initial state is just this much prompt, and then you took an action by generating Shanghai, and this defines your new state, right? This is your new state, your prompt and one word completion. Now here you take another action, that is generating age, you get new state, another action, new state, another action, right? So this can be your trajectory in case of language model, right? Now we talked about this already, like you do this log derivative trick. Now with trajectory, what changes? So you have now for the trajectory you are maximizing. So we say, okay, probability of trajectory given parameters times the reward model for the trajectory, right? Now you bring gradient under integral, and then you do the log derivative trick. So this becomes delta theta log p tau given theta, p tau given theta, r tau, right? This is very similar to what we did, right, in the previous case. There were no trajectory, now there are trajectories. Now you put back the expectation. So this is an expectation of this term, right? So this is expectation of, you sample trajectories, and this is what you try to maximize. Yes, and the probability of trajectory you can write as probability of the first action given the state, next action given the state, because everything else is independent, right? Going from one state to another state does not depend on theta. I mean, it you have an action, so given a state and an action, how do you go to S1? That's like deterministic, so it does not depend on theta. So the only thing that remains are, in a particular state you take an action, right? So the only thing that will remain here are AT given ST, right? Okay. Now if I want to approximate this expectation, I can say, okay, I will take some d sample and I'll compute this for all the samples, take an average, right, and then I will update my parameters. So you see this formula is very similar to the last formula. Earlier we were just talking about a single completion. Now we are seeing one token at a time. That's the only change. Reward is still at the entire trajectory level. Right? So this is the only change we have done from the formulation we did earlier. Right? We've said in terms of trajectories. Now, why are we doing that? I mean, how will this help? So one thing for sure, like how would you compute these log probabilities? That is easy because you have a transformer model. The RL model you are training is just a transformer model. You keep on passing very Shanghai, you keep on getting you do self attention, you get all these embeddings, right, at each layer, and you get the logits at the final layer. You apply softmax, you get the log probabilities, right, and that's what will give you the log probabilities. So log probability is easy because once you pass this, you get the log probabilities. Now how do you get the reward? Now reward is also easy because you have a reward model trained. So you can pass the input, the prompt, and the completion. You get a reward, right? So you have an input, completion, and because reward will give you at the last word, right? You get you apply a linear layer on the last embedding, the model dimension, and you get a scalar value. So I can get both log probability and I can also get the reward. Okay. So now, this is my expression. Now what is one problem with this expression? The one problem with this expression is that because of this quantity that you are saying that I will take it over some d samples, and typically people take very small number of samples. Ideally it is approximating an expectation, right? So it's over all possibilities, but you will only explore few of those, right? So what will happen because of that? Your gradient will have a high variance, right? I mean, depending on what subset d you have taken, you may go in this direction, that direction, another direction. So there will be high variance here, right? On an average it will still have the same value, but it will have high variance depending on which subset you take. So that's why PPO, what is done, you take some additional steps to ensure that your variance is reduced, right? So what are the steps that you take? So one thing is that, okay, so yeah, this bracket will come here. Yeah, so you have this quantity log pi theta, AT given ST, and R tau. What is R tau? The reward for the entire thing. So you started from state naught, take an action A naught, you get a reward R naught. You went to S1, you take an action A1, you get a reward R1, right? You may call here or wherever, right? Yeah. You can call this your reward 1, reward 2, whatever. You get the rewards, right? R tau is the total reward for the entire completion. So you can think of it as if you are getting from time t is equal to 0 capital T, every time you go from one state and take an action, you get a reward, right? State an action, you get a reward. You are accumulating all the rewards. But what is happening now at time step t, right? When you are taking an action, so you are at particular state, say ST, and you are taking an action AT. The reward you get should also only be in the future reward. You should not count the past reward at that time, right? So you can already start saying, okay, I'll go to ST plus 1, I'll get some reward. Maybe I'll call it RT plus 1 or R of STAT, whatever, right? I'll get some reward. So, but right now in this formulation, what is happening? I'm multiplying the whole reward, right? R1 plus R2 plus everything, even up to RT I'm adding. So why don't we remove that? So we say, okay, we only take reward from that point onwards up to the horizon, and this is what is called rewards to go. I only talk about rewards that are left now. This is rewards to go, starting from that time point to the final horizon, right? So this is one change we do. This will possibly remove some noise in my estimation. It will remove the variance. Then this is the expected reward I am thinking. if I start from here and I'll go up to the finite horizon. Now, what is on an average I'll get a reward? If I'm a current state, what is the expected reward if I take any average action, right? And this is what we call as the baseline, right? This will be dependent on the current state. In that state, what is the expected reward, right? So this does not consider the action, and this considers the action, right? Now this, if you remember the notation in the previous lecture, you will start connecting it to an advantage function, right? So this baseline, you can think of it as a value function, right? So that is, what is the future expected reward if the agent is in current state S and acts as per the policy, does not talk about the action, right? So this is the value function, and this is like a Q function, that if I am in a state and take an action, what is the reward I will get over the time, right? And Q minus value function becomes my advantage function. So this will what will become advantage function. So what is the idea of the value function? So suppose I am here, where is Shanghai is the prompt, I have generated Shanghai edge. Now we should expect the value for this state to be high, because this looks like a good completion. So whatever else, I mean, there is a high probability that I'll actually generate the correct answer. But on the other hand, if we are here, what is Shanghai? Chocolate muffins. This particular state should have a low value, right? I mean, this would not give me a correct answer, right? So that's how I can think about the value function. And the interesting thing is that this value function also can be trained. I can predict the value function. How? I can use the same language model that I am training, right? So I am anyway training it. So I know when I feed where is Shanghai, Shanghai is, I'll get something at the last layer of the transformer, right? The model dimension output. I'll use that to predict a value, just like I was doing for reward model. I use the same idea to predict a value. Okay, so I'll just predict a value at every time point from the final layer. I apply linear layer and predict a value, right? So you can approximate this V pi s, and this can be trained. This can be trained, yes, along with your model. Okay. So now just to complete what is done, so you have, so we were saying we will use this, and this actually was, and there is a baseline, and this you can see as a Q function minus value function, and this Q minus value we say it as the advantage function. Okay. Now, and this, what is the advantage function telling me? That how better it is to choose this particular action in this state compared to an average action, right? That's the definition of advantage function. So how better it is to choose a particular action A in state S over the average expectation we get by choosing any action randomly, right? Okay. So for example, if I am in this state, where is Shanghai, I can choose an action, take an action of Shanghai, I can take an action of generating chocolate, right? So one of these can be my action. So what will happen? See, Shanghai is ideally going to result in a good response, right? It has a more chance. So I should get a more advantage here. While chocolate will result in a bad response. So I should get a low reward. So that means the advantage I am getting here by taking this action Shanghai is higher, and advantage I am getting by taking the action chocolate should be lower, right? So accordingly the model will train. Okay. So now there is just one more detail, like fine, this is okay, we will try to get this and use that to update my parameters. The problem is that what we are doing, we are sampling trajectories right now from the same model, and we will update the parameters, right? So for every time we have to update the parameters, we have to sample trajectory from the same model, right? And we have to update many times, so this can be very, very inefficient, right? So how often would you sample trajectories? So there is a trick called importance sampling. So if you want to find expectation over a distribution, you can use a trick by going to another distribution for the same expectation. Like if you want to sample or find an expectation of fx as per distribution px, you can make use of a distribution qx for doing the same thing. How? So this is nothing but px fx expectation. Now let me multiply it by qx, numerator denominator. Now I'll take qx here, so I'll get px by qx, qx fx dx. Now you can think of it as if I am taking an expectation of Px over Qx fx over the distribution Qx, right. This can be written like that, and this is what is known as the importance sampling. That is, so now you think about, you wanted to do this for the online policy, but suppose you have an offline distribution. So Q is your offline distribution. So I can use an offline distribution to sample the trajectories. I get expectation from there, use that to compute the expectation, right. So this is what makes it very efficient. So and what is done in practice, I will show in the next slide. So what you can do, you can evaluate an expectation over a distribution x using samples from another distribution y, right. But in this case we do not have two copies of the same policy. What is happening? You are continuously training a policy, you freeze at some point of time, call it offline policy, sample trajectories from there, compute everything on the fly, right. What is the reward for this, what is the advantage for this, you compute that, and then you train your RL model. You train your RL model, right, to maximize that advantage, right. And once you have trained it for sufficient number of times, then you take this copy and update your offline copy, right, and then you sample more trajectories. So you do it at some point of time, not every time you have to sample a trajectory. Okay. So you have an offline policy, so some offline parameters, you sample trajectories from there, take a mini batch of trajectories and run gradient ascent to train parameters. Now again, after some epochs, you update your offline to online, and you keep on doing it for some epochs, and that is what is your off policy learning. Right. So now this can give us the overall PPO loss. So this you can see from the importance sampling formulation. So this is your the actual probability from the online model, and this is your offline model, AT given ST, and this is the advantage function that you are multiplying it. There is an interesting thing called clip. Why? What is the clip function will do? See, this pi theta online by offline will have some value, right. The probabilities, they will all be, I mean, say this will be positive, but it can become very high or very low. Clip is saying you clip it between 1 minus epsilon to 1 plus epsilon. So for example, if this is your function, let's say this is your function in terms of x, this is what is going. If you are clipping the function, so suppose this is 1 minus epsilon, this is 1 minus epsilon, and this is 1 plus epsilon. So what clip will do? So whenever it is beyond 1 plus epsilon, it will clip it to 1 plus epsilon, right. So it will clip it to 1 plus epsilon. Whenever it is below 1 minus epsilon, it will clip it to 1 minus epsilon. So it will not go beyond that range, so that you don't get a very high or very small value here, right. It's clipped between 1 minus epsilon to 1 plus epsilon and multiplied to the advantage term, right. That's what is the PPO loss. And for value function, what you do, how do you train the value function? You know what is the desired value and the value that you are getting from your model that you are training, and what is the value you get from the rewards, right. So you take an L2 loss to train your value function. There was a third thing that you also had, that is the entropy loss. So idea is that you don't want your model to restrict to certain kind of words only, you also want it to explore. So you want to have it to have slightly higher entropy, right. So promote diversity, promote a high entropy. So that's why you have an entropy loss also, and you have some weighting function for policy model, the value function and the entropy function, and that's how you train the PPO part. Okay. So we have I mean, in some in very short, we have discussed how is the PPO algorithm slightly different from the normal reinforced way because of using the advantage term, right. That while they just use the reward directly, reward minus scale divergence. Okay, and yeah, you can read from this book, and this particular GitHub repo also had some very nice illustration for this. Okay, so we will talk a bit more about this in the next lecture. We will also talk about another variation called direct preference optimization. Thank you.